changes of state. One simple one is, let's say you've got a glass beaker, lights. See? I think that's going to help. Sorry. Sorry, I can't seem to do anything about these lights. I think they're on emergency power. Okay, so this will just have to do. Okay, so when I think of a change of state, one thing that comes to mind is, let's say I've got a beaker full of sulfuric acid. Okay, just sulfuric acid is not something you want to get into, on your hands. And into this you drop a piece of metal. Right, and those of you who do chemistry, what you see is, what immediately happens is the metal dissolves. So it seems like, it looks like one of those vitamin tablets you put in water, it just fizzes, the metal dissolves. There's some gas coming off, there's some heat, this thing warms up. So clearly something changed along the way. We dropped metal into this acid, we got heat out of it, we got some sort of gas coming off, the metal disappeared. So clearly something changed, and we could measure this change by the mass of the metal that's left, the amount of gas that is released, the amount of heat that is released. So we can measure some sort of change occurring when we do this. Another change of state, for example, is, let's say I've got just a rubber block. And now I decide this rubber block, we're going to compress this. So I put it in some sort of vise and I compress it. So what happens is the rubber changes its shape. So it probably bulges out a bit over there. It contracts over there. So that's another measurable change of state. I can measure the shape of this rubber block, and I can see after compressing it, it has changed its shape. So I can measure this change of shape. And all of these things we just describe generally as changes of state. So if any physical thing, if it's got a certain property that changes, and I can measure that change, we say changed its state. Now, what I want to connect this with is this idea of energy. Those of you who know a bit of chemistry might tell me, but hold on, there's some sort of chemical potential energy because I get heat out. We all think of heat as energy. You know, if you've got a heater on in your room, it makes you feel nice and warm. We know we must burn a lot of coal to power big power stations like Eskom. So we know heat has something to do with energy. So clearly these systems have got some sort of energy. And I'm going to use an unofficial definition of energy for now, but just something to have you keep in mind. So I'm going to say energy is, we can think of it in terms of the following. If a system, so any physical system, does not change its state after, say, some time has passed, chances are it's got low energy. So think again of the student sitting here in front, sleeping. That student is not going to change his or her state during the course of this lecture, so that student probably has got low energy. However, if a system does change its state, after a certain time, or after the same amount of time, chances are that system has got more energy. So we still don't really know what energy is, but the idea is that we say, well, if things are changing, if in some measurable way, and it seems to happen kind of spontaneously, like the piece of metal that just dissolves in this acid and you get heat, there's some sort of energy associated with that. Whereas if I just have something sitting on a table and it does not heat up, it does not change its shape, it does not suddenly explode or break up, chances are that system doesn't have so much energy to utilize in any meaningful way. So energy has got something to do with the change of state. More energy means a larger change of state. Less energy means things kind of stay the same or tend to stay the same. Now, this really is an unofficial definition of energy, but it will suffice for now. So, if we look at what we have done so far in this course, we've only looked at one specific change of state. And that is if something starts at one position and it moves to a different position and it accelerates. Right? So that we can think of a change of state. So the only change of state we've looked at so far, so the only familiar change of state that we have really looked at so far is, let's say I've got a block and it's on a surface, and over here the block has got initial velocity equals to 0, and let's say we've now got a force acting on this block, and it's an unbalanced force, so it's a resultant force that's non-zero. We know Newton's second law tells us a force gives us acceleration, so this block will accelerate in that direction and it ends up over here, let's say a certain displacement, delta x away, and it now has a final velocity which is not equals to 0. Right, so how has this block changed its state? Well, we can say it changed, it was at one position, now it's at another position. So that's what change we can measure. It had no velocity, now suddenly it has got some velocity. So definitely the effect of a force, so having a force acting on this block, induces a change of state. Okay, so that's the first link we can make. So force on the block, that changes the state of the block. Now, if we think in terms of, let's say this is a 100 kilogram block of lead, right? And I happen to be standing right over here at this instant, and I see this massive block of lead coming towards me. Let's say over here it's already moving at 10 meters per second. Would you agree with me that that block of lead has got the potential to change my state rather drastically, from living to not so much? So, if the block of lead is just standing still, it doesn't really have the potential to affect my state. It's not going to collide with me, it's not going to hurt me in any way. So, somehow, if the block of lead gains velocity, it's moving faster and faster, it now has the potential to affect other objects. And the faster it goes, the more it has this potential to affect other objects, in this case me standing in front of it. If that was not a 100 kilogram block of lead, but instead we've got, let's say, a fly that weighs 0.001 kilograms, and it's flying at 10 meters per second, and I'm standing over there. Would that really, if the fly collides with me, except for the inconvenience of having to perhaps clean my face, would it really change my state in any significant way? Not by much. So we've got these two things. We know that, well, the larger the velocity of an object becomes, the more it can change the state of another object, in this case me. The larger its mass is, also the more of an effect it can have. And it somehow gains this potential to injure me or to change my state through a force acting on it. Right, so forces acting on objects, and if the only result is that the force increases the velocity of that object, somehow gives this object more of an opportunity to affect something else. So a force increases, in this case, the potential of the block to affect another object. And if we think of our unofficial definition of energy, we can say, well, somehow the force has transferred energy to the block. Because if the force was not there, we could wait and wait and wait and wait and wait, and that block would never do anything to me. However, once the force is there, now suddenly, if we wait long enough, that block can hurt me, it can change my state. So the addition of a force, in this particular case, implies some sort of transfer of energy to the block. So we've now got a link, right? We know vaguely what energy is about. We know now kind of what forces are all about. And we've now established that somehow forces increase energy, or they transfer energy. But we've got one little problem still. It's all fine to think in terms of blocks, but how can you think of describing, for example, a chemical reaction? So some sort of compound gets mixed with something else and you get different compounds out. So a chemical reaction, can you think of describing that in terms of forces acting on objects? It's difficult, right? Perhaps if you look at it microscopically, you can get kind of a model that works somehow, but really on a fundamental level, the whole idea of a force doesn't help you a lot to explain how chemical reactions work. Yet we know, I've got batteries powering this microphone, and they are delivering energy. So somehow I can utilize chemical reactions to get energy. So I can burn coal in a power plant to mechanically, in the end, turn a turbine. So I can use energy to put things into motion, but I cannot always think about forces, putting things into motion, and describe everything I see in nature by a force. But what we can probably do is we can describe most things we see in nature in terms of some sort of energy. Right? So forces have got a pretty limited application. It's difficult to describe a whole bunch of things with forces. Energy, on the other hand, is this great unifying thing. We can describe chemical reactions, we can describe things like how you boil food on a stovetop, we can describe blocks moving on surfaces, everything we know, we can describe in some way in terms of energy. So we know that if a battery delivers a certain energy output, I can convert that to a certain amount of motion, if you will, because of this idea of energy. If you didn't have energy, that type of equation or thinking would have been impossible.